is a study of mathematics, mental architect, and digital span. Take grade 5 students in Shandong province as an experimental subject. Our group members include Jennifer, Linda, and Mia. Let me introduce the introduction first. In introduction, we stated that working memory is described as a human cognitive center, playing an important role in complex cognitive activities, such as understanding, reasoning, problem solving, which is one of the most active areas of research in correct cognitive psychology and cognitive neuroscience. Mathematical problems, especially mental arithmetic, as an important thing, active and skill in people's daily life, has become an indispensable research topic in psychology. Combine working memory and mathematical mental arithmetic, it has been found that the capacity of the efficiency of working memory and executive functions playing a central role in mathematical skill development. Therefore, our study will continue to explore the relationship between working memory and mathematical mental arithmetic. Next, I will introduce it in 3 parts, namely working memory, central executive, and working memory and mathematics. First, working memory. There are 3 parts in the process of thinking in our brain that every educators need to attention. It includes attention, working memory, and long-term memory. This article mainly discusses the content related to working memory. The so-called working memory refers to the fact that when people want to complete a cognitive task, they must temporarily store information in a system during the completion process. This system is working memory. We can consider working memory as a temporary psychological platform. On the platform, people can perform a series of actions. For instance, processing and reorganizing information, all which activities can help people to carry out the more effective abilities of understanding language, making good decisions, and solutions to problems. Furthermore, working memory can be regarded as an information manufacturing factory as well. By processing the information people gain from daily life, people can code the information and choose to store them in long-term memory or delete them. Next is central executive. As shown in Bentley's working memory model, central executive, psychological loop, and visual-spatial scapepad constitute the whole model. The central executive is the core of the system. Its function is to coordinate the different functions of various systems in working memory, not only to control coding but to control information retrieval and the attention system at the same time. The psychological loop, on the other hand, can store and control wire-based information and can directly convey writing language and sanitary code. The visual spatial scapepad is responsible for storing and processing visual spatial information, consists of a visual system and a spatial system. Next is working memory and mathematics. Working memory is an important factor in mathematical performance. The storage function of working memory is limited in size. Individual parts of to-be learned information are organized into meaningful groupings, or we can call these groupings trunks, which has a common size of 7 blocks and can then be retrieved and unpacked at a renewal. People can usually only focus on one thing on this platform. If they do multiple things at the same time, it may affect their working, especially for primary school students. The cultivation of concentration is very necessary. In our study, we predicted that there is a significant correlation between primary school students. This has also been confirmed in Link's research. Link takes digital span as an indicator of working memory according to the figure of working memory which process and store information temporarily at the same time. In his study, it shows that in the most simple mental arithmetic processing, the digital working memory span is about 6 plus minus 2, and B, within 10 to 90 years old, the highest score of the test appears as the age of 16 to 19 groups, which are high school students groups. And the regression analysis shows that the digital working memory span will change in probably from the long with the age. And say compared with past research, digital working memory span is affected by mental arithmetic processing. And as mentioned about working memory can store information for a few seconds. To retain information longer, there is such a memory called long-term memory. So how we work memory to convert it into long-term memory? Why can I still remember so many things from a long time ago? Because this information is stored in long-term memory, thinking the mathematical mental achievement ability of experimental school students as an example, there is a gap among students' mental arithmetical ability. Relevant experimental studies have shown there are significant differences in the mental arithmetic performance of studies in different grades, and the mental arithmetic performance of senior grade is significantly higher than that of the lower grades. Studies need to retrieve information from long-term memory to help answer questions while they are doing mathematical experiments. If there is a problem with long-term memory like damage or the retrieval speed is slow, it will affect the speed of finishing task. Conclusion includes three types: coding, operation, and conclusion. If it is a relatively simple conclusion such as 2 plus 3 equals 5, we can directly see the result. This is the knowledge that we have deeply memorized in our long-term memory and can be extracted easily. Nevertheless, we need to follow the three steps to work out the complex and difficult conclusion problems. Numbers studies have shown that there is a close relationship between completing ability and numerical span. Some researchers have also proposed that working memory span is an indicator for evaluating working memory ability, indicator for evaluating cognitive ability. Okay, next, Mia, please.
Okay, thanks for Linda's introduction of the project, and I'm Mia. I will talk about the next part. Let's start with the purpose of the study. In 1981, Lin, a Chinese psychologist whose research on the development of the digital concepts and arithmetic capability of elementary school students, showed the developmental tendency of the capacity of generalization. And in 2010, Kibble put forward the potential relevance of a relationship between working memory and math for understanding developmental and individual differences in mathematical skills. So, based on these research studies, we finally narrowed down our research topic on the relationship between digit span and mathematical mental arithmetic speed in grade 5 students in China. About hypotheses, we have two hypotheses. Null hypothesis 1. There is no significant correlation between grade 5 students' digit span and mathematical mental arithmetic speed. Alternative hypothesis 1. There is a significant correlation between grade 5 students' digit span and mathematics mental arithmetic speed. Null hypothesis 2. Grade 5 students' digit span is not a significant predictor of their mathematics mental arithmetic speed. Alternative hypothesis 2. Grade 5 students' digit span is a significant predictor of their mathematics mental arithmetic speed. Our methods are mainly about three aspects: participants, digit span test, and mental arithmetic test. Participants were selected from students in grade 5 in a primary school in Shandong Province, China. The original data were 68 participants. 18 of them were screened out according to three criteria. Students who are trained in a special abacus were excluded. Students who have an obvious physical disease or mental disease were not involved. Students whose score were 2 standard deviations below the average were not considered. And in the digit span test, participants will have a group of numbers. The pairs of numbers are read out in a short amount of time by the examiner, and the participants are required to remember and report out what group numbers they have heard in a shorter period. For example, when the test begins, participants can hear a group of numbers 6, 8, 9. The other participants need to report these three numbers 6, 8, 9 successively. The test includes 10 groups of numbers, which start from 2 numbers in a group to 11 numbers in a group. Each group includes 3 pairs of numbers, and each pair of numbers will be read out once. If the participants can get 2 pairs of them correctly, they can pass this group and move to the next group. Mm, mm. And in the mental arithmetic task, there are 24 mental arithmetic questions combined by 5th grade mathematics textbook, which is Beijing Normal University edition. There are 3 levels of difficulty. Level A, add and subtract with the same denominator. Level B and Level C are both to add and subtract with the different denominators, but if you observe carefully, you can find some difference. The test has 3 difficulty levels, each of which has 8 questions, including addition and subtraction of fractions with a total of 24 problems. The mental arithmetic test can be seen in Table 2. Okay, that's all about purpose, hypothesis, and methods of our project. And next part will be introduced by Jennifer.
Okay, so now let's move to the analysis and results part. In this study, data were analyzed by SPS Statistics 26 software. The Shapiro-Wilk test was used to examine the normality of the dependent variable. Pearson correlation test was used to test the correlation between the two variables, and a linear regression analysis was performed to examine whether the length of the digital span was predictive of grade 5 students' mathematics mental arithmetic speed. We setting 0.05 as the alpha. If p-value is less or equal 0.05, we reject the null hypothesis. If the p-value is larger than 0.05, we fail to reject the null hypothesis. And look at this table. This is the descriptive analysis. The descriptive data for the scales adopted in the present study and reported in this table, we can find the digit span as a whole was wide. Mean is 8.12 and the standard deviation is 1.53. The average time of mental arithmetic speed was 2 minutes 74 seconds, and the standard deviation is 1.07. The normality test. From this picture, from picture 1, the histogram approximates a normal curve. In picture 2, the points fall more or less in a straight line. Thus, the scores of the criterion variable are normally distributed in the population for all levels of the predictor variable. And furthermore, in this table, the Shapiro-Wilk test of normality was conducted to determine whether digital span and mathematical mental arithmetic speed data are normally distributed. The results indicate that the data of digital span and mathematical mental arithmetic speed are both normally distributed, and which p-values are 0.053 and 0.073, which are all larger than 0.05. And let's look at the correlation test. In this table, there is a significantly negative moderate correlation between digital span length and grade 5 students' mathematics mental arithmetic speeds in the population. And R48 is negative 0.412, and the p-value is 0.003, which is less than 0.01. The R-square is 0.170. Thus, it shows that the null hypothesis 1 is rejected. And now let's move to the regression test. Look at the scatter plot. The scatter plot is randomly and even distributed around 0. Thus, the scores of the criterion variable are assumed to have the same variance in the population for all levels of the predictor variable. And now let's look at the ANOVA test coefficients and model summary. According to these data reports, we can tell that simple linear regression is used to assess the ability of the predictor, which is digital span, to predict the criterion, which is mental arithmetic speed. Preliminary analysis were conducted to ensure that there is no violation of the assumptions of normality, linearity, independence, multicollinearity, and homoscedasticity. In this table, we can tell that digital span is a significant predictor, and F148 is 9.811. The p-value is 0.003. This also shows the predictor beta value is negative 0.412. P-value is 0.003. From the analysis in the third table, the degree of freedom value adjusted R-square is 0.152, indicates that approximately 15.2% of the variance in grade 5 students' mathematics mental arithmetic speed is associated with the variance in digital span length. Thus, it shows that the null hypothesis 2 is rejected. Digital span length is a significant predictor of grade 5 students' mathematical mental arithmetic speed. And now let's look at the conclusion of this paper. According to the empirical study, what we have done, the essential findings from our research are that depending upon the analysis result, there is a significantly negative moderate correlation between digital span length and grade 5 students' mathematical mental arithmetic speed in the population, which means that if a grade 5 student has a wide digit span, he or she can finish mathematical mental arithmetic tests in a shorter time. Moreover, grade 5 students' mathematics mental arithmetic speed is associated with a variance in digital span length. However, the impact didn't carry a huge percentage of the influence. And now, let's look at the general discussion and limitation of this paper. Overall, the study demonstrates that the digital span has a negative moderate correlation with grade 5 students' mathematical mental arithmetic speed. The wider digit span, the shorter time of them to finish the tasks. Secondly, it shows that generally 15.2% of the variance in students' mental arithmetic speed is associated with the variance in digital span, which is not a large proportion. From these findings, there are a few limitations of the current study that could inform future research on people's mathematical mental arithmetic ability and working memory. Because we assess the experimental outcomes in a small group which is limited in Shandong province, China, considering there is an education gap among students in different cities, the participation selection should be included in more cities. To explore more mental process between working memory and mathematic mental arithmetic ability, future studies need to contain more and other factors, for instance, visual span, verbal span, spatial span, and so on. Okay, so this is all the report of our research. That's all. Thank you.